In this video, we are going to learn how to use double angle and half angle formulas to establish identities. So I put my power reducing formulas at the top of the paper here as nice references as I go through establishing identities. So for our first example, we want to write an equivalent expression for cosine to the fourth of theta that does not involve any powers of sine or cosine greater than 1. This is where those power reducing formulas really come into play. So I'm going to write cosine to the fourth of theta. And to show how I can use this formula with cosine to the fourth of theta, is that this expression can be rewritten as cosine squared of theta, and that whole expression is squared. So there's that cosine squared of theta. So now I can replace cosine squared of theta with 1 plus cosine of 2 theta all over 2 squared. And now, in order to square this, one thing that's going to make my life a little easier in terms of squaring is I'm going to factor out that 1/2. But when I factor out the 1/2, it's also going to be squared. And then I'll just square 1 plus cosine of 2 theta. So now, whenever I go to square, I'll just have 1/4 times 1 plus cosine of 2 theta squared, which is a binomial squared, so I could square the 1, give me 1. Then I can double 1 times cosine of 2 theta since they're going to be multiplied together twice. So it'll be plus 2 cosine of 2 theta. And then it'll be cosine squared of 2 theta since it'll be multiplied by itself. Cosine squared of 2 theta. And then I could redistribute that 1/4. Give me 1/4 plus 1/2 of cosine of 2 theta plus 1/4 of cosine squared of 2 theta. So now we've already gotten down to a cosine to the first power, but we still have a cosine to the second power as well, which I could still reduce using the same formula. So again, replacing this theta with 2 theta, I can get 1/4 plus 1/2 of cosine of 2 theta plus 1/4 times, using this formula, 1 plus cosine of 2 times 2 theta, since now I'm using that as my theta, all over 2. So now if I were to put 1 over 2 by itself, I get 1/4 plus 1/2 of cosine of 2 theta. Here I'll have 1/4 times 1/2, which gives me 1/8, plus 1/4 times cosine of 4 theta over 2, which gives me cosine of 4 theta over 8. So if you saw there, this little split of 2 terms just came from that one fraction. I just thought of it as 1/2 and then cosine over 2. And now I can do 1/4 plus 1/8, giving me 3/8, plus a 1/2 cosine of 2 theta, and then plus a final 1/8 of cosine of 4 theta. And now we have no more powers for sine or cosine, so this expression has reduced the power down to 1. So that's a big reason why they call those power reducing formulas. Now let's establish a few identities as well. So here I have cosine to the fourth minus sine to the fourth is equal to cosine of 2 theta. So reasonably, we have another formula, a double angle formula for cosine. So here what I can do is actually start with the cosine to the fourth of theta minus sine to the fourth of theta. And I can actually use this difference of 2 squares, because this can also be seen as cosine squared of theta squared, just like we saw up here, minus sine squared of theta squared So now we have a difference of two squares, so we can use conjugates to split them up. So we can get cosine squared of theta minus sine squared of theta times its conjugate cosine squared theta plus sine squared theta. And now I see here, this is just 1. That's that Pythagorean identity, which I'll write here to remind you. The Pythagorean identity is sine squared of theta plus cosine squared of theta is equal to 1. So I'll now have cosine squared of theta minus sine squared of theta times 1. And here's my double angle formula for cosine. Since I know that cosine of 2 theta is equal to cosine squared theta minus sine squared theta. And that's how you establish that identity. Now let's establish this identity. Tangent of v over 2 is equal to cosecant of v minus cotangent of v. So here I have a half angle formula for tangents, which I'll write as tangent of alpha over 2 down here. And I knew 3 of these. One of them involved the square roots, but that doesn't seem to really help me with my final answer. But the other 2 were 1 minus cosine of alpha over sine of alpha, and the other one was sine of alpha over 1 plus cosine of alpha. So I'm going to start with my tangents of v over 2 for my solution. But now I need to pick which one of these half angle formulas works better for my case. So if I keep the end in mind, I know that cosecant is the reciprocal of sine, so 1 over sine of v. And cotangents can be written as the quotient of cosine of v over sine of v. So if I think about that, they both have a denominator of sine. So this formula on the left is really appealing to me since it only has a denominator of sine, while the other one has a denominator of 1 plus cosine of alpha. So I'm going to use this half angle formula, giving me 1 minus cosine of v instead, since that's the angle, over sine of v. And now they have a common denominator, so I can rewrite this as 1 over sine of v minus cosine of v over sine of v, which brings up the reciprocal identity for cosecant and the quotient identity for cotangents, thus proving my identity. Now lastly, I'm going to show you another way you can use the power reducing formulas. So here I have cosine is equal to 1 minus tangent squared of theta over 2 over 1 plus tangent squared of theta over 2. So this is the more complicated side, so I'm going to start with that one. So 1 minus tangent squared of theta over 2 over 1 plus tangent squared of theta over 2. So now there is no power in my final answer here. So I need to reduce these powers, which I'm going to use the tangent squared power reducing formula for. So I'll get 1 minus 1 minus, because it's going to be a fraction, cosine of 2 times theta, but theta in this case is theta over 2. Which would just simplify to theta. So I'll have 1 plus cosine of theta over 1 minus cosine of theta over 1 plus cosine, again, of just theta, since we're doing 2 times that angle. And then in my denominator, I'll have 1 plus the fraction 1 minus cosine of theta over 1 plus the cosine of theta. And now I am dealing with a complex fraction. My answer certainly doesn't have 1 in it. So I'm going to multiply my numerator by 1 plus cosine of theta and my denominator by 1 plus cosine of theta. In this way, I'll cancel out that denominator, leaving me with 1 plus cosine of theta times 1. So that's just 1 plus cosine of theta, minus what's left in my numerator, because these canceled out. So 1 minus cosine of theta, all over, again, 1 plus cosine theta times 1 gives me 1 plus cosine theta, plus what's left in my numerator, because the 1 plus cosine theta is canceled, 1 minus cosine of theta. And now if I distribute this negative, I can start to simplify. So I have 1 minus 1, which is 0, and cosine of theta minus negative cosine of theta, so that's cosine of theta plus cosine of theta, so 2 cosine of theta, over 1 plus 1, which is 2, and then cosine of theta plus negative cosine of theta, which is 0, leaving me with 2 cosine of theta over 2, which just reduces to cosine of theta, which is what I was going for. So that's another way you can use those power reducing formulas in a more creative way. And that is how you use double angle and half angle formulas to establish identities.